Namaskar students. In this video, we will check a problem on the concept of generating function and the recurrent relation. Here, with the help of generating function, we will be solving a recurrent relation. So let us briefly discuss that what is a generating function. Suppose we have a sequence A0, A1, A2, A3, so on. And we are defining its generating function. The notation which we are using here and we will be using in this problem for the generating function is this function will be denoted by this capital G. This is the function of t. It is defined with the help of the sequence A0, the first term of the sequence. Then we have A1t. Then we have A2, the second term of the sequence, A2t square. Then A3t cube, so on. So this is the generating function for the sequence AI. So here the problem is we have to solve the recurrence relation with the help of generating functions satisfying the initial conditions A0 is equal to 1, the first term is equal to 1, and A1, the second term, is 2. The recurrence relation which we have to solve here, if we check its nature, it is a linear recurrence relation and it is non-homogeneous in nature because the right-hand side is here 2. This is the linear recurrence relation with constant coefficients. We can see here that the coefficients are 1, then -5, then 6. And this is recurrence relation of order 2. The highest subscript which is involved here is r plus 2, and the minimum one, the lowest one which is involved here, that is r. And if we take the difference of these two, we will be getting 2. So this recurrence relation has order 2. So firstly, let us consider the generating function. So let us assume generating function as gt. And gt is given by, if you write down this series in the summation form, this is the summation. If you take the summation on r, this is the summation of this product AR t raised to power r, and this r, it is from 0 to infinity. So firstly, we will be multiplying this equation 1 with t raised to power r on both sides. So multiplying equation 1 with t raised to power r, we get here, this is r plus 2th term of the sequence. Then in the product, now we have t raised to power r, then we have -5, then we have r plus 1th term of the sequence, then we have t raised to power r plus 6, then we have rth term of the sequence AR, t raised to power r, and similarly on the right hand side we have 2 t raised to power r. Now let us check here that for what minimum value of r, all the terms which are present here, all the terms of the sequence here which are present here, they are valid, they are defined. So if we consider r as 0, then this will become A2, the second term of the sequence. If we consider r as here we consider r as 0, it will become a1 and this will become a0. So all the terms are defined for r equal to 0. So we will be taking now the summation, and we will be taking here the summation from r equal to 0 to infinity. So let us name this equation as equation 2. Summing equation 2 from r equal to 0 to r equal to infinity, we have, let us take here the summation. Summation is from r equal to 0 to infinity. This is ar plus 2 t raised to power r. This minus 5, we can take it outside of the summation. R is from 0 to infinity. A r plus 1 t raised to power r. We can take the 6 outside. R is from 0 to infinity. AR t raised to power r. And here again we have summation from 0 to infinity to t raised to power r. Now let us open this series and we will be trying to introduce here the generating function g. So if we see these sums, if we consider here r as 0, it will become a2. If we consider r as 1, it will become a3, t, a4, t square, so on. Then we have minus 5. If I consider here r as 0, then it will be a1. The next term of this sum will be a2, t, a3, t square, so on. Then we have plus 6. If we take r as 0 here, a0 t raised to power 0, it will be a0. Then we have a1t, a2 t square, and this series here, it is the series of, here this 2 we can take outside because this 2 is free from this r, and the summation is on r is from 0 to infinity, t raised to power r. Now let us try to write it in the terms of generating function. See here we have a2, but with a2 we need a2t square. Similarly with a3 we need t cube. So let us multiply and divide with t square, and after that we need a0 and a1t. So we will be adding a0 and a1t and we will be subtracting the same terms. Similarly here, we need a1t, we need a2t square, a3t cube. So we will be multiplying and dividing with t. And after multiplying and dividing with t, a0 is still missing. So we will be adding a0, a1t, a2t square, a3 t cube, and minus a0. So this one, a0 plus a1t plus a2t square plus a3t cube, this is our generating function. So I am writing here that directly that we have here the generating function gt, and this is minus a0. Then we have plus 6. And if we see this sum a0 plus a1t plus a2t square, then this is the generating function, this function g. And on the right hand side, we have 2. And this summation, the series is the series of 1 plus t square. And this is a series of 1 upon 1 minus t. So here, if we collect the coefficients of GT, then it will be 1 upon T square, and we have minus 5 by T, then we have plus G. And let us put here the value of A0 and A1 as it is given in the problem that A0 is here 1 and A1 is given in the problem that A1 is 2. So let us use these two values here. We have collected the terms of GT, and here we have minus 1 upon T square. A0 is 1, this is 1, and A1 is 2. So it will be 1 plus 2T. And similarly, this minus 5 by T and minus A0, it will give us 5 by T, if we put here A0 as 1, and all other terms we have considered here in GT. And this series on the right hand side is the series of 1 upon 1 minus T. Now let us simplify, let us try to find here GT. So if we take here this GT and we take here the LCM as T square, then it will become 1 minus 5T plus 6T square. And on the right hand side, we have 1 upon T square, 1 plus 2T. Then we have minus 5 by T. And we have, already we have here in the right hand side, this term 2 upon 1 minus T. So we have here GT. And if we factorize the numerator here, 1 minus 5T plus 6T square, then we will be getting here the factors as 1 minus 2T, 1 minus 3T, and here we have T square. And here if we take the LCM, here we can take the LCM as T square, so it is 1 plus 2T, and this is minus 5T, and this is 2 upon 1 minus T. So if we simplify it further, this will give us GT. We have these two factors, 1 minus 2T, 1 minus 3T, this divided by T square. And if we, this is 1 minus 3T, 1 minus T, further simplifying the right hand side, this is 2T square, and here it is T square, 1 minus T. So this implies, if we solve it further, this T square on both sides, they will cancel out, and we will get that this GT is equal to, if we simplify this numerator on the right hand side, it will give us 5T square minus 4T plus 1. And here we have 1 minus T, 1 minus 2T, 1 minus 3T. Now, from the recurrence relation, we have converted it into the generating function, this function G. And then we have here evaluated, we have seen that what is GT. We have separated here to GT. Now, with the help of partial fractions, we will be simplifying our right-hand side. If we see the right-hand side in the denominator, we have linear factors, 1 minus T, 1 minus 2T, and 1 minus 3T. So if we talk about the partial fractions, the partial fraction, they will be of this form, A upon 1 minus T plus B upon 1 minus 2T plus C upon 1 minus 3T. So we will be considering these partial fractions, and once we will be finding and checking for these A, B, and C, here A will come as 1, B will come as minus 1, and the C will come again as 1. So easily you all know that how to find out the partial fractions. So by that method, you will be finding these partial fractions. By partial fractions, this GT will reduce to three fractions, they will be 1 upon 1 minus t, because we are saying here that if we have this partial fraction, the partial fraction will be having this form because these three factors, they are linear in nature, and these constants a, b, c we will be getting as 1, minus 1 and 1. So the next will be here b is minus 1, so b is minus 1, 1 minus 2t, and c is 1 upon 1 minus 3t. So this is our generating function, and once we have the generating function, we will be writing the series corresponding to all these three expressions. For 1 upon 1 minus t, we have the series 1 plus t square, then we have plus t cube, so on. Then we have minus sign, and for 1 upon 1 minus 2t, we have 1 plus 2t, then we have 2t whole square, we will be having the powers of 2t, and we have 2t whole cube, and then we have 1 plus 3t whole square, 3t whole cube, so on. Now, if we see here the coefficient of t raised to power r, if we try to write it in the summation, where the summation is an r from 0 to infinity, then it can be written as 1 minus 2 raised to power r. We have here the minus sign, and then we have 3 raised to power r, and we have then product, we have 3 raised to power r. So if we compare it with the form of generating function, because generating function, this is given by the summation ar t raised to power r. So here this coefficient of t raised to power r, this one, this is our rth term of the sequence. So we get here that the rth term of the sequence, this is 1 minus 2 raised to power r plus 3 raised to power r. So in this way, with the help of generating function, we have solved here the recurrence relation. Here we will be needing some initial condition depending on the order of our recurrence relation, as here the order is 2. So we have here two initial conditions, A0 as 1 and A1 as 2. So what we have done from the recurrence relation, we will be multiplying it with t raised to power r, and we will be taking here the summation. We will be deciding that from where we have to start the summation, for what value of r we will be starting the summation. And after that, we will be writing all these series in terms of generating function, as we have done here. But we have tried to convert this in terms of our generating function gt. And after this, we have separated the gt. On the left hand side, we have just gt, and on the right hand side, we have a polynomial rational function in t. Then with the help of partial fraction approach, we have evaluated the partial fraction, because once we have partial fraction, then easily we can find out that what will be the coefficient of t raised to power r in this particular rational function. So here, and this is the way that how we will be solving the recurrence relation with the help of generating function. Thank you. Have a nice day.